Hello. Hey, well, my hair is still messy-ish, but okay, yeah, good. Hey, yeah. So we did this rehearsal yesterday. It was very scuffed. Hey, so let's try it again today. Also, I sorry about like pushing things back again. Like half an hour. My stomach was upset and still is upset. I feel like it always happens on the day of a like any talk that I give. Oh wow, I am hearing multiple copies of myself. Let me see. Why is it? Oh, because this is up. Yeah. Okay. So what was I saying? Yeah. But I mean, it's why it is, right? But let's actually just yeah, let's actually give this another try. Hopefully, it's better than yesterday. Yeah. I mean, the talk is in like 2 hours, so if it's still not good, then I don't know what can I do at this point. But yeah. So the talk is on quantum fair exchange. Let's just start. Oh, I probably need a stopwatch again. Hey, by the way, I hope the sound volume is okay. Let me check. Hey, okay. I think the sound volume might be okay. Actually, maybe I should just let me see. I need to speak a little bit louder, right? Or maybe do I get a little bit closer? I don't feel like shouting. Maybe I can just do this. Can I just do this? Hey, no, it really should be a like I it'd be really funny if I just like do like this whispery thing. Like I mean, I guess I'm not like really whispering, but yeah. What if I? Oh wow, that is very loud. The oh right, there's this like square root law or whatever, right? Basically, the when you are closer to your mic, then you actually pick up a square root, not the. I mean, when you are going farther or closer to a mic, like the volume is scaled to a square root instead of linearly. So the thing decays very quickly depending on how close are you to your mic. So if I do this, then then it's just gonna be naturally loud, I think. I mean, I don't know. Like right now, okay, yeah, maybe the other thing is I don't have a pop filter, right? So I feel like certain syllables is just going to sound worse if I try to be very close to a mic. Sorry, I'm just like speaking while monitoring this and see what is going on here. Hey, maybe I'll just pretend this is good. Yeah. I mean, at least my voice monitor feels like it sounds good at my in my ears. So maybe I will just pretend this is good and start. Yeah. So yeah, Quantum Fair Exchange is the project. It is a joint work with Hao Zhong at Layer Zero. Uh, this is myself at student in Maryland, and Justin at NET Research, and Aravind at the University of Sydney, where I'm visiting right now. My audience probably knows him. Not you guys, but the actual audience later today. Yeah. Okay, so fair exchange, that is what we are starting today. So let me try to describe the setting here. So we have this cryptography setting where we always have Alice and Bob. We have two people. Let's say Alice has some money. She's trying to buy something from Bob. For example, maybe digital ticket. You can think of it as either a ticket for a concert, or you can think of it as anything else that's digital. For example, maybe some like video game serial code or some gift card serial code. Hey, actually, I on the video game side, I remember there was this other term that I was using, but I forgot. Anyways, yeah, the activation code, yeah, video game like activation code or license, or the what is it called, or gift card a serialization code, yeah. So Alice wants to buy it from Bob, but the problem is that well, this is a cryptography talk, so people can cheat. So if Alice pays first, then Bob can take the money and disappear, and just logs off and nowhere to be found. And same here, if Bob sends the ticket, Alice can just take a ticket and refuses to pay. Yeah. So I mean, of course, the obvious solution to this problem is that you do have a trusted third party. So, for example, like what we are, in real life, where we are doing this today, we do have like banks and credit card networks, right? So Alice would, the bank has Alice's money, and then Alice pays Bob using a credit card, and then Bob sends a ticket. But if Bob does not send a ticket, then Alice can kind of dispute and do chargebacks, and we are fine. Yeah, but then in this cryptography setting, we are sometimes we ask this question: if what if there's this like cash-like? Can we do a cash-like exchange? For example, can Alice and Bob exchange directly anyways without using this credit card network or this trusted third party? And well, I guess the next natural question is why is this important, right? Well, turns out that there are some notions of digital cash out there that people actually care about. Well, both this like blockchain cryptocurrency setting and this quantum money setting, these two are both important settings. They are trying to solve different problems, but maybe I can describe both of them today. After I blow my nose because this allergy is still, uh, yeah. One moment. Uh, Good. Sorry, I was having trouble unmuting. I also realized I'm not so good at whispering into a mic, so now I still sound normal, but that is fine because I'm trying to give a. Maybe the point today is to give a cryptography talk, anyways. It's not to whisper into a mic. I can try it next time. Or maybe I can try it today now. No, this doesn't work, right? Oh, this kind of works. Yeah. Anyways, that's too loud. Yeah. Eh, um, yeah, anyways, let's just get on with this. So, what was I doing here? Okay, yeah. So let's talk about this like blockchain cryptocurrency setting. So what they want, their goal, their selling point, I guess value proposition. Not saying that I agree or disagree. I'm just describing as it is. I have plenty to say about it after the talk. You guys can find me sometime. Yeah, but for now, their proposition is this entire idea of this like decentralization. Basically, they don't want government to be printing money because the problem is that well, the government can be printing a lot and a lot of money, and then this very nice thing called inflation happens, and in a few years, your money is worth nothing. And also they don't want this like centralized credit card processing system to basically uh not the processing system, I mean what's the term here, agency, not agency, a network, yeah. You don't want this like credit card network like Visa or MasterCard to tell you what you can or cannot spend your money on. So this is kind of what they care about, this decentralization thing, where you kind of don't need to go through any central entity. That is their goal, one of their goals at least. Yeah, and because of that, now you have to, if you want to print money, then you have to do some like maybe cryptocurrency mining or other thing like proof of stake or whatever. But the idea is basically just that for printing money, you cannot rely on central party to print it. Yeah, and to transfer money, well, this is a little bit less convenient than our usual, what is it called? Um, from our daily life of a transferring money and spending money. For example, they might take a little bit more time, might take a little bit more transaction fees and stuff like that, but they can do it. They have their own, a payment system. Basically, just create a new block on the blockchain, and in terms of security, I mean, of course, cryptography talk, right? So we always have this kind of like security thing. Basically, for example, you don't want some kind of bug where I spend my money today and then I spend the same $20 bill tomorrow. Like I cannot, double spend. I cannot create fake money like counterfeit this kind of thing. There's basically always security. Yeah. And then turns out that in this classical as opposed to quantum, this classical setting, you already have fair exchange. For example, there's atomic swaps, smart contracts, and other nice features. And blow my nose again. Sorry. Okay, yeah. So where are we? Hey, okay, so in the quantum money thing, by the way, like yesterday, I was looking at my VOD yesterday, and I was kind of lagging quite a bit. I mean, the voice was fine, but the what is it called? Oh wow! And also, monitoring my thing on my other device, my hair looks so messy. I probably should be tying it back. But oh well, I guess it's what it is. Yeah. The other thing is I even put some stuff like, what is it called? Even put this thing in my hair, like this kind of a hair, what is it called? Conditioner lotion thing. But it just doesn't really help. Like, it feels like so messy. Anyways, yeah. Quantum money. So basically, they don't really care about decentralization in their setting. You still have a bank, and transfer is still as simple as possible. You want to spend money, just send the money to somebody else. But they do care about security in terms of no cloning. So the idea is that, well, if you have a $20 bill or whatever, then, well, people do make fake monies out there, counterfeit. I mean, if your tech is good enough, then of course you have a good enough copy printer or whatever you can try, right? And people have tried and people have gotten caught. But anyways, yeah. And the selling point, I guess their main feature for quantum money is that because there's this thing called quantum no cloning theorem. I wonder if the people in the audience today have heard about it or not. But basically, because there's this no cloning theorem, that makes they are relying on this no cloning property to make it so that you cannot clone money, so you cannot create fake ones, basically. Yeah. So that is kind of their idea here. But then the question today is that can you have quantum fair exchange? And that is what we are going to study today. But let's actually be a little bit more concrete on what fair exchange is. So there's this schematic, this interface, or this like as cryptography people call it, this ideal functionality. Basically, Alice will send her money, and Bob sends his money into this box, and then this box will check if these monies are valid, and if they are both actual money, then you swap them. Yeah. Eh, uh oh, I keep forgetting the other fine, maybe I can also say that I probably should be saying this earlier, but the other motivation is that, well, I mean, of course, cryptocurrency, right? Like, why, or maybe this is a good place to say, like, why are they changing money? Well, maybe one way to think about it is that, let's say, maybe this is Bitcoin and this is Ethereum or whatever, basically money on different blockchains, and they want to change it, maybe. Yeah. I also forgot that I can also say one is a secret key, but anyways, that is besides the point. Maybe don't want to say that. That's too low level. Yeah, maybe like different cryptocurrency is fine. Yeah. So now, eh, um, let me put my nose again. Okay, yeah. So, let me see. So in classical fair exchange, Bob can of course try to cheat because this is cryptography that we are talking about today. And if Bob cheats, then Alice gets reject. Then Alice knows that the thing has rejected, and Bob has not gotten anything. Bob has not gotten her money because Bob, gave nothing. Should receive nothing. Yeah. Wait, my rash is acting up. Let me try to mute and put lotion on it. Oh, I don't need to. I don't need to mute. I can just put lotion on this. Let me see. Yeah, this is fine. Yeah. Yeah, it was the rash that I was talking about yesterday. I feel like this is like basically a problem. That's when I get a rash, it just never heals because like a like rash is like itchy, right? So like I scratch it and it just gets worse. Yeah, and so it's like I basically never had this rash in Taiwan, but now for whatever reason I started getting it, and then like near my neck, and then it just never heals. Also because my necklace on top of it. Yeah. But anyways, yeah, let's actually get on with this. So, yeah. So Bob have given nothing. He should receive nothing, and Alice should know Bob has cheated. That is the idea here. But then, if you want to just generalize this to the quantum setting, then you have a problem here. Because, well, earlier we said there is this no cloning theorem, right? So let's say if Alice puts her money in this box and Bob has cheats again, then if we only reject, then that's a problem. Well, Alice does not have another copy of her money. So here she just lost her money, and that is really bad. Yeah, I mean, Bob gets nothing, but Alice has lost her money. That is still unfair intuitively. So what we want in a quantum setting is actually this: that if Bob has cheated, then Alice should get her money back. That is the what we want to achieve for the talk today, or in the project rather. Okay, so now let's do a little bit of storytelling. So classical fair exchange has been studied for decades. I I will make some excuse. In fact, it's not even a good excuse. Uh, as yesterday, but basically I don't know that much literature. My co-authors know a lot more. At some point I will learn. Yeah, just not ready here yet. I guess the only valid excuse is that this is ongoing project, so I'm not. But no, I don't know. Yeah, and then the on the quantum side, there are definitely some research on the concept of fairness. Mm, wait, I let me drink tea. Sorry. Yeah. Hey, oh, by the way, like this is like because I don't have an actual cup. Now I'm having just making 冷泡茶 for everything. Yeah, and it takes forever to brew, but it tastes fine. Yeah, I have so many different kinds of tea. Actually, maybe like should I show you guys? So I have this from this one from Alishan. It's actually my grandpa's friend gave it to us. And then I have this Guihua version, which is also really nice. And then I also have this, which is like kind of pricey, but it smells so nice. And then I also have some tea bags. I don't know where I put them, but well, yeah. I mean, I cannot make tea bags out of this anyways. Yeah, because I don't know, in my head tea bags always hot water. Anyways, yeah. Let's oh wow, my neck. Oh, lotions before we continue. Yeah, okay. So this idea of fairness has also been studied in the quantum setting, but it is mostly in the multi-party quantum computation setting to be more precise. But then what they've achieved is mostly identifiable abort, which means if a protocol fails, then at least actually I don't think I need to even say this. Like maybe I can say this. Say twice, no need. Yeah, okay. So, sorry. Yeah. eh, uh, what was I saying? Yeah. So basically, whoever cheats can be caught. But I mean, it's a little bit less important in this in our setting today because there are only two players. So if Alice has cheated, then Bob well knows that Alice is the one who cheated because there's nobody else. Yeah, but that is kind of the current like one of the current research directions. There's this paper by Allen, Bar Allen and Kaimin Zhong, and this is one of the our co-authors today, Hao Zhong, a Miriam Huang, a student of Kaimin at the time. Actually, Hao Zhong was also student of Kaimin at the time, and myself, student of Kaimin at the time. Yu Qingsheng, also student of Kaimin at the time. Yeah, and then this other work makes this thing called public identifiable uh, adds this public identifiable feature that maybe I don't have the maybe all the scope of the talk today, but come in again, mean again, and Cheng Tang, basically I mean also coming student, and then Jia Peng Zhang, which is means a PhD advisor. Ming has graduated, so I guess former advisor now. I don't have to say that. Yeah, and then the other piece of very important like I guess technology, I guess, that kind of underlies this entire line of literature is this verifiable quantum homomorphic encryption. Basically, this and our project is all built on top of this. A so I mean, like, how should I say this? I mean, I guess I'm also wondering how much of my audience have heard about homomorphic encryption, but basically I think they have, right? Because this like Godel Prize 2022, right? And then homomorphic encryption, yeah, like yeah, Godel Prize 2022 homomorphic encryption. So yeah, it's a pretty big thing. I mean, not the quantum version, the classical version. But basically, I mean, if people don't know, I probably would just draw on the whiteboard, but probably not right now. But basically, yeah, the usual client server stuff, and you have a quantum version, and you also want a verifiable version because you want to make sure that the server is not misbehaving here today. Yeah, you want to make sure. Yeah, right. Okay, maybe that's all I have to say here. In terms of yeah, maybe in one sentence summary, the server cannot misbehave without getting caught. Yeah. Okay. But then in all of these settings, we have this thing where identifying a cheater does not return the honest party's quantum input, and that is what we are trying to achieve today. Yeah. Okay. So contributions, we define quantum pair exchange. We aim to show two complementary results. By the way, this slide has been new and improved. If you have classical trusted third party, unfortunately, I will just show today that classical like sorry, quantum fair exchange is just impossible in general. Yeah, but then if you allow quantum trusted third party, well, if you allow a fully quantum one, then everything is again trivial because you can just send everything to a trusted party verifies and swap the states. But then it turns out that if we have a limited quantum trust party, then it turns out you only need quantum storage and preprocessing. You don't need any like online quantum resource. I mean, you don't need to do any online quantum computation. I guess the story was that initially the kind of weakest assumption you have is this if you allow only quantum storage, can you make it work? And we tried for a bit, we couldn't manage to make it work, so we also allow preprocessing because this is just what a some kind of like weakening of the like compromise that people are willing to make out there. So this is kind of an ideal situation, and this is kind of a compromise that we had to make this to make a protocol work. Yeah. Okay, so impossibility result. So if you assume that there is a T round fair exchange protocol with a classical trusted third party that that does a fair exchange, then well it turns out there's a reduction to quantum cloning. I guess this is a I'm wondering again if my audience has know about quantum cloning, but if not, then this is maybe around where I will have to give a whiteboard lecture. But basically, yeah, the probability of a cloning one money is this. But then because we know that this thing cannot be cloned, or we don't expect this to be clonable, so then that is a contradiction. So therefore, the usual reduction thing, that means this thing cannot exist. Yeah. Okay, so the intuition behind the reduction is suppose the exchange happens in round t for some lowercase t, some number between 1 and big T. Then you choose this at random, you guess the round, you guess t, and you guess this with probability 1 over t. Then you can kind of make strange things happen. So basically, the strange things being that, well, in this round, you guess, you basically let this message through, but you drop this message. So let's say if you guess the round correctly, then this is what you will see. Well, I mean, in this case, Alice has sent her input, but is now left with nothing. So we expect the situation to be unfair. So we would have expected the protocol, the fair exchange to be broken. But then let's suppose that we still have fairness. Then, well, if it's no recovery, then it's not fair. But then if Alice rejects, then we kind of expect that assume for the sake of contradiction that the protocol is fair, Alice must get something back. But then on the other hand, because you've already sent this, then Bob also accepts this. So now you suddenly have two copies of this. You have cloned. That is kind of the intuition here. The actual proof is a little bit more tricky because the actual exchange you cannot really as easily pinpoint when the exchange has taken place because Alice and Bob can kind of send this, for example, this can be a lot of qubits and this can also be encoded and they can send the money kind of like piece by piece across a lot of different rounds. So you cannot just say, so like what does it mean to guess the round correctly? The and like you need to actually carefully write down the probability of getting two copies of this. So yeah, that is the analysis, but the intuition is basically just this. Yeah, I mean the intuition and the actual reduction is pretty much just this. Yeah. Okay. So this is on the impossibility our impossibility result. I mean, the other thing is that we are brushing the existence of the trusted party under a rug, but I mean, there are also messages to a trusted party, right? So we also have to do something there to make sure everything works. Yeah. But up to those caveats, things work. So now, maybe I should be taking questions here, but basically, yeah, I mean, you guys can write in the chat, write in the comments or whatever. It doesn't really matter. I mean, or just find me when I'm live one of these days, and you guys, yeah. Mm. But anyways, let's move on. So, yeah. So feasibility, what we show, like on the feasibility side, so we have a protocol that satisfies priority-based security. At least we have the simplest, the easiest one is correctness. Basically, if both parties are honest, then they accept and receive each other's states. I probably don't have to say that they accept. But fine, that is fine. Yeah. And then we have soundness, which is that an honest party, let's say if one party cheats, then the other honest party would always live with a valid state. If protocol accepts, then the party gets the other inputs. Otherwise, on reject, it at least gets its own money back. Yeah, so this is what we've achieved. We don't have composable security yet. We are working on that. Yeah, so this also has to do with like maybe privacy and this other abstract concept of the composability. This is just hard in general, like harder than this in general. But this is some cryptography nonsense that my audience today is anyways not cryptographers, so they maybe don't need to worry too much about this like ideal functionality or this like simulator kind of nonsense. Yeah. But anyway, so we can already talk a little bit about this protocol sketch. So step one is how we call input encoding. Basically, Alice would send her money into this like sub protocol. We will build this later, but then this sub protocol is supposed to output this encryption of her money to a quantum trusted third party, where this T ink is the verifiable quantum fully homomorphic encryption FHE that I was talking about earlier. So why is it T ink? This you guys will see in a moment, but basically it's just the encryption from earlier, the verifiable quantum FHE encryption. Yeah, and then now because this is homomorphic encryption, so now your next step is basically to let Bob checks this you by doing this homomorphic encryption to check if this money is valid. But then we also need this like idea of this verified evaluation. So if Bob tries to cheat during this evaluation while checking if this is valid, then well, for example, you cannot just send this entire thing to Bob because he drops it. Then you just lose your money and it's game over. So instead of that, you need to do this interactive verified evaluation where you are kind of you are kind of verifying this piece of money like piece by piece, and you want to catch a cheating bot before this is a damage beyond repair. Yeah. So that is kind of the intuitive idea. So now but yeah, I mean, this is kind of two main phases, but there are a lot of black boxes here. So, like for example, what is this doing and what is this doing? So let's actually open the black boxes and actually talk about the actual construction here, the building blocks. So the first building block is quantum error correction. Here this will actually just use as a black box. I'm not going to say how to build this, but basically you can have a state, you can encode it. This is not encrypt, it's encode. There's the difference here, like, yeah, this thing is encoded. I mean, the difference is basically as, as it sounds that, well, yeah, it's not encrypted. A scene is readable. This is readable. Yeah, and then like there's no secret here. Yeah, okay. This arrow is a little bit bothering me. Like there's only an arrowhead. There's no there's no arrow body. But oh well, yeah. This is just the usual stuff we have to deal with. Yeah, and then let's say you have a lot of okay, so you encode this into many pieces, and let's say you lose some of the pieces. Either you lose them or there's some attack on top of them, and then you decode. It turns out you still get the original thing back as long as you haven't lost that many. One key point here is that this entire thing is a entangled block. Oh, physical qubit is just their terminology. Basically, it just means that this is like logical qubit, this is physical qubit, but don't mind this term too much. It's just the yeah, what they call encoded qubits. Yeah, encoded means physical in the in their community. Yeah. So now the key point here is that this entire thing is entangled. We are not making just n copies of this because, well, you cannot because there's no cloning. Yeah, okay. So, but anyways, yeah. So you can actually, I don't know if I needed this. Maybe not. Yeah, but the yeah, maybe I can say I don't need one code block. Sorry about the clickety clackities because same as yesterday, my mic is on top of my keyboard, my laptop. Yeah. But anyways, yeah. So yeah, maybe I should be a little bit closer to the mic because of this. Because I'm really not speaking very loud right now. Because low energy and because stomach upset. Yeah. But yeah, so you can correct up to some. You choose some number lambda, and bigger lambda is intuitively you should expect that this is also unique and is also bigger. Let's go with lambda. Yeah, but if you have you pick a lambda and then you can say that if the attack damages at most lambda positions, then this decoding will be successful. This is kind of interface. Again, I don't plan on explaining how this is built, but we just use this as a building block. Yeah. Okay, and another property of this building block is that it allows these transversal operations. You can just think of this as homomorphic operations if you are more on the crypto side. It's just different terminology for different communities. But yeah, so let's say, for example, let's say we are doing this C0 gate. This is one of the quantum logic gates, like quantum gates in quantum circuits. This is called control knot or control X because basically, you know, on the first bit is a control bit. If this is 0, then the second bit has not changed. But if the first bit is 1, then you are negating the second bit. So 1 0 maps to 1 1 and 1 1 maps to 1 0. That is how C naught is. And turns out that a lot of QEC constructions have this natural homomorphism uh, with C naught. So basically, maybe here's the equation version. Basically, that you have this QC encoding, and you hit everything with C naught like this. Then that is the same thing as you first hitting with a C naught, and then you do encoding. So there's this like a what is it called? It's like, I guess, mathematical term is that this thing respects C naught operator. Yeah. So I mean, this doesn't. There's this general property that this doesn't support basically like you don't get all gates for free. Like for example, I don't know how many people know about RSA, and this might be also a little bit like sidetrack, but basically like RSA like supports like I forgot which operation was it for free, like multiplication or something. But yeah, like you always have this like natural homomorphism, natural partial homomorphisms, and this is just kind of how you always like the kind of things you get, or I shouldn't say for free, but the kind of thing you have. Yeah. Stomach upset, very sad. Yeah, but anyways, okay. Another piece of background is the quantum authentication, because this is we are kind of trying to build towards the VQFHE right now. So basically, we have this a so authentication consists of key generation, encryption, and verified decryption. These are just the interface here. So I mean key generation. So now we are actually in cryptography land now, where we have like key generation, encryption, and verified decryption. And when you are encrypting and decrypting, you always need key, so need key generation. Yeah. Okay, so this is, I guess, the typical picture of how you would use an authentication. Basically, you have, sorry, my hand is like bothering me a little bit. I just put lotion on it as well instead of like picking at it. Yeah, but basically you have, oh, my hair. Anyways, yeah. So you have this typical client server setting, and the client can do this keygen, and then and encrypt his or her input, encrypt however he wants, basically, and then he sends it to a server, his encrypted version, and server kind of holds on to it, or a server can kind of attack the state, might get, might return something the same or something a little bit different, and then the client can try to decrypt it, and then basically gets either some output or he rejects. The security of authentication means that this thing should not be modified. So if you accept, then it should be then you should expect that this is close to this, and this closeness is the usual, like inverse exponential thing. Yeah. So you can just say this is like maybe exactly the same, basically. Yeah, up to some low probability of failure. Anyways, yeah, that is a besides low probability of the server guessing your state, guessing your key, uh, guessing your key. Yeah, but anyways, yeah, a yeah. So now let's build this. A so trap code. So we want to set key generation as well. The key is a permutation together with two strings. Turns out that is enough. Well, I mean, this is just one-time pad, a one-time pad encryption key, as you guys will see. That will, the actual encryption is that you take the state, you put it under quantum error correction, you append what we call traps. This is why it's called trap code. We shuffle them, or I guess the put a random permutation. I mean, this is this permutation, so we kind of permute them. So the bad guy doesn't sorry. So the bad guy, namely a server, does not know which qubit is a data and which qubit is a trap. And to make actually sure of that, because this is not encrypted, neither is this. You just encrypt it with this one-time pad. Yeah, so that is kind of an intuition here. Sorry, I was, yeah, keep forgetting that and speak a little bit too loud. But anyways, yeah, this is kind of the what is it called? The intuition here, that the server will not be able to hit too many position of this before he hits one of this and gets rejected. And because you have a error correcting code here, if the server gets lucky and actually hit this once or twice, then this should be like correctable. Yeah. So verified decryption basically, just works as as you might guess. You undo this and this, and then you measure and check this. And if this, if this looks bad, then you just reject. Otherwise, you peel this away and you output this. Yeah. Okay. So that is kind of how this is. This is our QAS, our quantum authentication scheme. And now finally we have VQFHE, which basically you guys can just think of as a homomorphic operation on trap code. But let's actually get the interface right and the big picture right before we actually fill in that construction. So VQFHE, it is basically, the interface is similar to in fact, the interface is, oh, I guess not the same because you have Vertex, but fine, similar enough to a usual homomorphic encryption. Basically, you do keygen as always because you have a public key encryption scheme. In fact, like this is symmetric key, this is public key. I probably should also, yeah. Anyways, now you have public key encryption. Now it's great. Yeah. Actually, I don't know if it's great, but fine. Let's pretend it's great. Yeah. Okay. So you have this keygen, you have encryption, you have decryption, and because you are homomorphic, now you have evaluation. Yeah. Okay. So now on the client side, you basically generate some key, and then you encrypt this. In fact, like because the public key is quantum, I probably should not be using the same symbol here and here. But that is, I'm going to brush that under a rug and just say that fine, the client has some input, the client encrypts it and sends the public key, the ciphertext, to a server as well as some circuit that he wants applied. And the server basically evaluates the circuit on the encrypted input, like what you would do on a homomorphic encryption. The server gets some encrypted output, sends it back to a client. The client will decrypt it. You probably find decryption also need to remember the circuit. Why not? Yeah. Eh, um, and then you get some output or rejection, and the security is basically similar as before, but also this like with this homomorphic thing back in. Basically, like if you accept, then this is close, up to this inverse exponential probability of again the server able to guess your secret key. But assuming the server has not guessed your secret key, then this is the same the as what the client wants, the circuit X on the input that he has. Yeah, okay. So now let's talk about how to build this thing. So basically you build this by basically let me just talk about CNOT again. So it turns out that if you have two trap code ciphertext, then you can just hit this entire thing with CNOT and it will work, assuming that they share the same permutation. So assuming the traps all line up, traps being red, and data lines up, data being blue, then assuming everything lines up, then CNOT across the entire thing, qubit by qubit, would actually be good enough. So let me say why. Because, well, okay, let's do this mathematically, and then senpai different one-time pads. So first step is that if you hit this entire thing with C naught, then C naught actually swaps with this quite well because like one-time pad is this one-time pad is naturally homomorphic with respect to C naught. So you have this homomorphism, you can just swap them. And then now you have C naught X on this permutation thing, but because earlier what we say earlier, the permutation is the same, so all the data lines up and the traps lines up. So this permutation does not really do much with against this C naught, like this just works. Yeah, and then now we think about we have C naught X on all three registers. Well, it turns well. I mean, what we said earlier. Basically, this respects C naught, so we can do this. And now we have C naught of our data. That is fine. How about C naught of 00 and this? Well, earlier we know that C naught 00 is 00, so it does not perturb the traps. And it turns out the same is goes for this trap as well. Well, why? I'm going to brush it under a rug and just, I mean, it's the two-line calculation, but I would just say, trust me, this is a case. Yeah, okay. So this is why you have homomorphic C naught. If you want the universal gate set, then you need to invoke this paper and actually look at how this public key and secret key are constructed. But that is kind of it. Yeah. Okay. So now we have all the building blocks, and like 5 minutes, we can also talk about our construction. Yeah, maybe I should Now that I know that I will be over time, maybe later I need to say a little bit faster. But okay, input encoding. In fact, our construction is small. It is like simple, so maybe this is still fine. Yeah. So input encoding, we are doing this teleportation trick that people know and love. Basically, I can first say how is it built, and then I can say why. Okay. So trusted party prepares this EPR pair, and the trusted party encrypts half of it using T-Ink, and then trusted party sends the unencrypted half to Alice. And because we have EPRs, this allows Alice to teleport her state to the TTP, and now TTP has this. So the point here is that we are not letting Alice to do her own T-Ink, because if she did, then she could cheat and do a incorrect T-Ink, and then things become very annoying to analyze. So by doing this teleportation, we can assume this T-Ink is a actual good T-Ink, and the only possible attack is to teleport the wrong state in teleport garbage, but you still have T-Ink, a good T-Ink of some garbage. Yeah, okay. That is maybe the input encoding part. So far so good. Okay, so now a homomorphic gate evaluation. Now this is a little bit. This looks very what is it called, scary. But let me try to just say what is going on here piece by piece. So you have some data that is under QEC, because earlier we have trap code encoding. So if you take this apart, then you have a piece of QEC and you have some traps, yeah. So by the way, this is only a single piece of the QEC quantum error correction. We are not sending this is not the entire thing, because if you send the entire thing, Bob drops it, it's again game over and you'll be very sad. Yeah. So you are only taking only parts of the QEC, and you again have some traps, and you do the usual trap code thing. You permute them, you encrypt them, and then you send this entire thing to Bob. And well, I mean, this thing is homomorphic, right? So you do just this gate on all of this. Yeah. So next, what you want to do is just to check if Bob is honest. So you want to just measure these traps to know if this is and see if this looks right. But the problem is that you cannot, because you are classical. Well, you're not classical, but you are not quantum enough to do measurements, because you only have quantum storage. So here the trick is to let Alice measure for you, but then you are also worried about a malicious Alice doing some funny things. So a so here's what you do here. So you take the trap from Bob, but you also add a little bit more traps to add for Alice. So this is to catch a malicious Bob, because this is these traps here. But you also add fresh traps to kind of check against if Alice is honest. Well, this are already one-time padded, so that is fine. But you also need a new dual permutation here, and same with the other trap type. Yeah, Alice measures it for you, and trusted party checks. And yeah, I mean, if these are all correct, then just keep this, and you do this for every piece of QEC, and now you have a gate. I mean, this is homomorphic, so you can swap this. I mean, this is not always homomorphic. Like to be able to swap this inside the one-time pad, that is the VQFHE thing that I'm brushing under the rug right now, and I will keep brushing it under the rug. But yeah, this is kind of what you have. On the other hand, you check this. Well, if this looks wrong, then you know for a fact that Alice has cheated, and the protocol can stop there. Eh, uh, if this is wrong, then you actually don't know who's cheated yet. So you have to kind of do some statistics. If this is always wrong, but this is never wrong, then at some point you know Bob has cheated. Yeah, so this is the intuitive construction here, but it turns out that we still have trouble proving that this is secure. Because math is hard. But then it turns out there's this common trick, this common re-encryption trick that people like to do in this cryptography thing. just for the sake of making things easier to analyze. The idea is basically you just stack multiple encryptions on top of each other's, just encrypt it over and over again, and somehow that makes things easier. I mean, I'm out of time, so I will not be able to say why. Maybe I will not be able to say why anyways, because this is quantum crypto, and I will have to start writing a lot of linear algebra on the board, and we hate to see linear algebra, or I don't know, at least like maybe the audience theory people supposedly don't hate linear algebra, but I don't know, we hate linear algebra around here. Yeah. Anyways, so you send a you send the extra encryption key here, and the and Bob basically just encrypts everything again. Yeah, so it's just one-time pad it again. So now you have two one-time pads stacked on top of each others here. So you have one-time pad number one, one-time pad number two. Yeah, and then the rest of the protocol basically just kind of a you just adjust it accordingly. So that is kind of how you evaluate one gate. Yeah. So now how do you evaluate a circuit? Well, basically the idea is that you just do this for every gate, but it turns out that that is also hard to analyze because now only Bob is doing the encryption, which means now, like if Alice is malicious, it's somehow easier to analyze now because Bob is re-encrypting. But this does not protect against a malicious Bob because Bob knows the encryption key. So basically, you just want to do this both sides. So for every gate, you have to actually have to break into two gates. You are for every gate you are doing the actual gate, and you are padding it with an identity gate that does nothing. But you want to take a mirror image of the above protocol. So it turns out for every gate you have to do this twice. Once let Bob do the gate, and then you let the Alice apply identity gate because that way both Bob does re-encryption and Alice also does re-encryption. Because the idea is again that if Bob is able to re-encrypt, then it makes it harder for Alice to cheat, and vice versa. If we allow Alice to re-encrypt here, then it makes how should I say it? Then it makes harder for Bob to cheat. Yeah, like here or in the next round for the next gate. Yeah. So that is the idea here, the construction here for each gate. We run this twice. Alice and Bob changing roles. You take this mirror image here. Yeah. Okay. Good. So now, finally the for exchange again, basically input encoding, and then you run this circuit. You run this other circuit. You check both money is good. Third party waiting for both verification results. If both accept, then you exchange them. Otherwise, you just send the money back. And this is the construction here. I mean, to prove that this is secure, I'm basically not doing any math today, but the math is tricky, hard. Actually, not so hard. Uh, tedious. Yeah. Okay. Good. So now, maybe to summarize everything, and also remember that the claim I had earlier that we can do pre-processing. So the trustee party have to prepare all of this offline. Wait, this is not right. This should be T ink plus, not plus T ink T. Yeah, I don't know why this is a yeah, this should be T ink of T, not T ink of plus. Yeah. Anyway, so this is the trustee party prepares the EPR pair for input encoding, prepares the VQFH evaluation key that I was brushing under a rock because for some gates things get trickier, and then you need traps and you need more traps, and if you can pre-process all of this, then in the online phase when during the actual protocol it turns out you can do just storage and communication is enough, and for routing, like permutation is only a swap gate, which is as classical as it gets. You also need to check the traps. That's classical and key update because you're re-encrypting. You need to do a bunch of bookkeeping. That's also classical. That is basically it. Yeah. Okay. So that is the talk, and I'm still like 10 minutes over. Okay. Good. Thank you all. I will make my voice code changes and then and head out to for the real deal, wish me luck. Again, like if you have any questions, then leave comments or just ask when I do one of the programming streams or something like when I'm streaming. Yeah. Anyway, yeah. So thank you. I will see you next time.